After some weeks of focusing on making the IoTT stick ready and available in the Tindy shop, it was time to pick up some loose ends from previous videos and have some fun building stuff. In this video I use a TF Mini Plus LiDAR to make a software-defined sensor device and start looking into various concepts for layout automation. Welcome to the IoTT channel. I am Hans Tanner. Here are the loose ends I am talking about. In video number 40 about at point versus in area detectors, I started to do an introduction to layout automation concepts, but gave up because I had difficulties to find the right balance between too detailed and too complex. In the comments to this video, channel viewer Clark Gregory asked for some pointers on how to connect his relay controlled layout using JMRI scripting. Here's what he wrote. I have a layout I take to shows that has a loop with a hidden passing track. While the rest of the layout is DCC, this is analog. Using reed switches and relays, I have a shade that comes from behind trees and brings loaded log cars to the logging camp. After it disappears behind the camp, a hazler brings empties back to the woods. Running analog is simple. A reed switch at entry on track 1 closes a relay that sustains itself and is a reversing switch to the loop. The trains go in opposite direction. The loaded one to the sawmill, the empties go from the mill back to the woods. A reed switch on track 2 releases the relay. A diode to each track stops the incoming train while the other train makes the trip. That all works beautifully, but I would like to do this with JMRI scripting. So here we have the perfect example for experimenting with some layout control concepts. Simple and easy to understand, but complex enough that train control is needed, and my plan is to start with the current analog concept and then step by step bringing it to where Clark wants to go. The second loose end I try to pick up is from video number 35, where I used the VL53L1X LiDAR sensor to build a multi-section block detector. At the end of the video I mentioned the TF Mini Plus LiDAR as the next level of evolution that could make the sensor better. And I talked about mounting it on a servo so that it can be pointed to different track sections. This sort of creates a software-defined sensor device where the number and location of blocks as well as the type of the detector becomes programmable. If it works, it would be ideal to bring block detection to a temporary layout because there is no need for isolated track sections with dozens of individual feeder wires and so on. With those two problems in mind, the idea for this video was born. Build a temporary sawmill layout as suggested by Clark and then use the software definable sensor to try out different layout automation concepts, starting with the analog concept Clark is using right now. In future videos this then can be changed to DCC and JMRI scripting as we go. So if you are interested in this type of content, then it is a good time right now to subscribe to the IoTT channel and hit the bell icon so that you will be in a premium seat when more videos become available. Here is the concept for the DC controlled layout as used by Clark. The main loop with a hidden siding for the two trains. The hazler travels in one direction, the shay in the other, leaving the impression to the viewer that one train is hauling logs while the other brings the empties. The travel direction change is achieved by changing the polarity on the track, and one rail in each siding is isolated and powered by a diode which prevents the waiting train from starting while the other train is on the loop. When the traveling train arrives in its waiting track, a reed switch is used to trigger the relay and change the polarity of the track, and the other train starts its loop. Note that with this concept there is always one train moving. The only way to stop it is pulling the plug to the power supply. What I am trying to do in this video is substituting all control system elements by an Arduino connected to a LiDAR sensor and a relay board. And just for better visualization, I also connected to LocoNet so I can easily verify the sensor statuses and the polarity. Those are relatively simple tasks, so I try to do it with an Arduino Nano, and I am going to do it step by step so you can see and understand the inner workings of the software. Here are the components I plan to use. An Arduino Nano board. The Nano board is more or less identical with the Arduino Uno, but has a much smaller footprint, that's why I prefer it. The TF Mini Plus sensor. This is a LiDAR sensor with a measuring distance of up to 10 meters according to the datasheet. More important, the opening angle of the laser beam is small, so it should be possible to detect a locomotive, I would hope, when it is about 10 feet away. We will see. An SG90 servo to mount the sensor on. The idea is to rotate the servo and point the sensor to various locations, then give each location a different block number, and therefore this will be a multi-block detector that can be configured in software. And by choosing what messages to send, it can act as at point or in area detector, actually both at the same time if needed. A dual SPDT relay which allows for changing the polarity of the track. This could be done just in the software based on the input from the TF Mini. However, since I like open systems, I prefer to also send block detector information to LocoNet, so that I can have some LEDs somewhere else. And in the other direction, I'd like to connect the relay to a switch address, so that I can change the polarity from a handheld throttle. For this reason, I add a LocoNet interface to the project, along with a Grove port jumper cable, so that I can use it with a breadboard. That's it, so let's connect the components together and see how to control them from the Arduino Nano. First, let's connect the relay board. On the high power side, we connect the DC power supply to the outside contacts of each relay, and the two center contacts of the relays go to the track feeder. Depending on the relay position, each rail is either connected to DC plus or ground, and the locomotive will move in one or the other direction, or it will stop if both rails carry the same potential. The control side of the relay is connected to 5 volts and ground of the Arduino, and the control inputs IN1 and IN2 are connected to IO pins 11 and 12. To test the relay, we can load a standard Arduino example program. Pick Examples Digital Blink Without Delay from the IDE menu system. Now we add 2 lines to define the control inputs for the relay and initialize them as output pins in the setup function. Finally, we add them to the loop function, compile and upload the code to the Nano, and there we go. The 2 relays are switching every second. By the way, I chose this example because it also shows an important programming principle. Never use the delay function in your main loop. Have a look how the 1 second delay is realized in this example. It is defined in line 43 as interval of 1000 milliseconds. In the main loop, we read the current number of milliseconds in line 60 and calculate the time that has passed since the last relay activation. If this value is greater than the defined interval, we process the relay activation, otherwise we just loop. I did not measure it, but on a Nano we should loop around 30,000 times for every relay activation, which basically is processor capacity that can be used for other things. If we would use a delay function between the relay activations, the processor would just be sitting there doing nothing. Not a problem in this case, but if you have other stuff to do, you would lose valuable performance. Therefore, if you are a less experienced programmer, I recommend to study this simple principle of avoiding delay functions, as you will use it over and over again. With the relay working, I connect now the LocoNet Interface module. On the one side I connect LocoNet, obviously, and on the other the growth port jumper cable. 5 volt and ground go to 5 volt and ground of the Arduino, and the white and yellow wires, which are transmit and receive, go to I/O pins 7 and 8 of the Arduino. Note that the receive pin must go to pin number 8, as the LocoNet library makes use of a special interrupt input of the Arduino, which only is available on I/O pin 8. The transmit pin can be chosen as you wish. However, I usually use just the next input, as I like to keep related things together. You can now install the LocoNet library in the Arduino IDE and pick the LocoNet monitor example from the example list. Before you run the example program, you should go to the Arduino library folder, find the LocoNet library and find the lnconfig.h file in the utility directory. In that file, uncomment line 75 to make the receiving pin working in inverted mode. Check video number 43 for a detailed explanation of this function. Now you can run the example, open the monitor, and you will see the LocoNet messages flowing. And just for fun, we can quickly change the example into a decoder for our relay. To do so, define and initialize the 2 relay control pins as we did in the last example. Also define the transmit pin and the switch number you want to use to control the relay. Finally, add the relay activation commands in the switch request callback function, which gets executed every time a switch command is received. Of course, we filter for the desired switch address and activate the relays based on the incoming switch position. Compile and run, and you are able to control the relay from your handheld throttle. Yes, it's that simple. Next, we connect and test the TF Mini Plus sensor. As before, 5 volt and ground go to the respective pins of the Arduino Nano. Transmit and receive we connect to I/O pins 3 and 2, but this is not critical. Luckily, someone has already done the hard work for us, and we can download a TF Mini library for Arduino from GitHub. The link is in the description below. Download and install the library in your Arduino IDE. Then load the TFMP example sketch that comes with the library. When loaded, you should activate the software serial option and initialize software serial with the transmit and receive pins 3 and 2 as shown. Further down in the setup function, you need to replace the hardware serial port by the software serial information. When done, you can compile and upload, and you will see distance readings appear in the monitor window, so the sensor works. After playing just a little bit with it, I must say it is actually quite accurate, so I am confident that it will meet my expectations. So far so good. Now for the servo. A single servo can be connected just using a PWM output of the Arduino and then be driven using the servo.h library. The servo is connected to 5 volt and ground and the data input to I/O pin number 9 of the Nano. Then install the servo.h library from the IDE Library Manager. When installed, you can load the sweep example, which is ready to go for a single servo connected to pin 9. Run it, and you see the servo making slow 180-degree turns back and forth. By the way, it would be a good exercise for you to change this example program to have the same functionality, but without those 15 milliseconds delay commands. So, that works, but there is a problem which becomes visible when we include the LocoNet library into the sketch. Servo.h and LocoNet.h are not compatible. I did not dig into the code to figure out what causes the conflict, because both libraries are using highly time-critical functions, so I have some doubts that the problem can be fixed. Instead, I simply changed my approach and used the PCA9685 module to drive this servo. It is kind of overkill, as this module can drive up to 16 servos, but it works reliably, as I have seen when making the 16-channel servo decoder back in video number 17. The PCA9685 module is connected to analog ports 4 and 5, which are the predefined I2 pins of the Nano. To drive it, we can use the Adafruit servo library, which can be installed using the Arduino IDE. The servo example that comes with the library drives servos 1 through 8 sequentially, so we can upload it to verify that the I2C connection to the module is working as it should. And with that, we have all modules connected and tested and can write the sketch that integrates everything. The process is rather simple. The sensor is placed on a servo in a location where it can measure the distance to each area where I want to know if there is a train there. In the case of the logging layout, this is a section of track 1 and a section of track 2. The trick is to find a location for the sensor where the view cannot be blocked by another train, so I chose a location along the axis between the two tracks. For this example, I only have to scan 2 points that are close to each other, but potentially from this point it is also possible to scan most of the track, which I will try to do in future videos. The sketch is relatively simple and straightforward. As always, if you would like to play with it for yourself, you can download it from my GitHub page listed below. First, I just list all the libraries and definitions by copying everything from the test examples. Next, I define some constants. Servo min and servo max are the limits of the servo movement. Rod speed is the approximate number of increments the servo can move in 1 second. It is used to calculate the time it takes to reach a new position, and a new readout can take place. Dist interval is the minimum wait time between two sensor readings, and dist read time is the time of the last read command. Servo channel, of course, is the output of the PCA9685 used to control the servo. Sensor index is the number of the sensor position that is currently in process. Await servo pause time is the expected time when the current move of the servo is complete, and servo pause is the last servo position the servo was sent to. All sensor data is held in an array with one entry for every sensor position, defining the servo position, minimum and maximum distances that constitute an occupied status, the current distance sensor data, and the block detector address to be used. A new data flag indicates if new information is available, and the last level variable has the information which block detector status was sent out the last time. All sensor positions are then defined in the sensor list. For the current project, I am just using 2 positions which serve as substitutes for the read switches, so one points to a place in track 1, the other to a place in track 2. The setup function initializes all devices and moves the servo to the angle of the first sensor position. Note that the entire TF Mini initialization is moved into a function located in the 3rd tab of the program and is simply called from the setup function. I like to put module-specific functions into separate tabs. It helps to keep the code clean and makes it easier to find a particular function when debugging. All functions below the setup function are part of the main loop of the sketch. The first one is receive LocoNet. It checks if a new LocoNet message is available and processes it. As seen in the LocoNet monitor example, some callback functions are called depending on the type of message. They are located in the 2nd tab of the sketch. As in the example before, we find here the activation of the relay if a switch command to the defined address is received. And the first 2 functions in this tab are used to send messages to LocoNet. The first one is to send block detector messages, the second for switch messages. These functions are only there to let the outside world know about what's going on. Just for this sensor, we could do without them. The command servo pause function tells a servo to go to a certain location. It then calculates the time the servo needs to go from the current position to the new angle and returns the expected time of arrival in milliseconds. Process servo read does the majority of the sensor processing. It first checks if the servo has arrived at the new position. If so, it checks if the TF Mini Plus is ready to receive the next reading command. If all is positive, we first issue a read command to empty out the data buffer so we get a fresh value for the distance. Then we call it again to get the latest distance reading. Once we get a valid reading, we store the data in the sensor list for the respective sensor position, set the new data flag and command the servo to move to the next location of the next sensor. The ETA for that new location is then stored in await servo pause time so that it can be used for comparison for the next location. Process input data is the counterpart to process servo reading. It goes through the list of sensor positions and checks for new data. If available, it figures out if the block is occupied or not based on the distance readings. The result is then compared to the last conclusion, and if there is a difference, a block detector message is sent to LocoNet indicating the new occupancy status. It then also calls the local processing function, which is used to send the switch commands that trigger the relay, but only in case of a transition from unoccupied to occupied, as we emulate an at-point sensor. Also note that we only send out the switch command to LocoNet. The actual activation of the relay happens in the notification function, which is called by the LocoNet library when the successfully transmitted message is received back from LocoNet. This is actually an important principle when doing LocoNet messaging. You always should broadcast your messages first to LocoNet and only take action on the echo. That way you make sure that you only process messages that were successfully sent to all other nodes, and if there is no echo, you can react to the error and resend. And with all that said, the main loop of the sketch becomes really simple. All we do is checking LocoNet for input, then progress the sensor reading process, check LocoNet again and process the received data. The only reason that I call the receive LocoNet function twice in the loop is that the process servo reading function may take a while, and I want to make sure that incoming messages are processed before I transmit anything to LocoNet. From a performance point of view, this is no problem at all, as the receive LocoNet function returns very quickly if there is no new message available. That's all, folks, so let's put it to work. For testing, I built a G-scale track with a siding and placed the sensor as explained next to one of the switches. Unfortunately, I do not have a Hazler and a Shay, but for the purpose of this test, 2 locomotives of the Swiss Régien Railway will do as well. To better visualize what's going on, I placed an IoTT stick with a blue hat between the 2 tracks of the siding and connected an 8x8 LED matrix to it. I configured it to receive LocoNet messages via MQTT. It shows occupancy status of both tracks with a yellow line next to each track and a big arrow in the middle of the panel changing between blue and red based on the track polarity. This first video clip shows the TF Mini Plus mounted on the servo and oscillating between the 2 defined positions. In each position it just stops long enough to measure the distance to the first obstacle and then goes on. As you can see, the number of readings for this application is more than enough. However, it will be interesting to see what sensor response times we get when we have, say, 10 sensor positions and a total angle of maybe 120 degrees. But I think we still should get more than 1 reading per second per sensor, which probably will do the trick. In this clip we see the system at work. A train arrives and triggers the sensor. the polarity is switched, the train stops and the train in the opposite direction starts moving. When it comes back from the loop, the same process happens and the first train does its loop. Note that the sensor is triggered when the measurement of the sensor is between specified minimum and maximum, so it really detects the end of the train in track 2. If I add a car to the locomotive, the train will automatically advance a little further before it stops. Here we see the LED panel driven by the Bluehead module. The yellow LED line parallel to the track shows the occupancy status of the adjacent track. The arrow in the middle changes color and direction based on the track polarity, hence the travel direction of the train. Interesting to note that the occupancy LED of track 1 goes dark for a short moment when the train on track 2 is approaching. This happens when the approaching locomotive crosses through the viewing field for the track 1 position and the train in track 1 can no longer be seen. Since occupancy is defined by minimum and maximum values, it shows unoccupied when the measurement is less than the specified minimum. This could potentially be a problem, but not in this application as long as the correct status comes back before the train in track 2 is detected. This is clearly the case here based on the geometry and location of the distance sensor. And here a clip showing the crossing from the cab level. And because it is so cool, the same just from the other side. So in general it works, but I also came across some problems. The first you see right here. This collision happened because the sensor was triggered too early. I investigated further and found out that the distance value returned by the sensor might not be very accurate if only a part of the viewing cone is covered. So when the incoming train enters the cone while approaching track 2 and the measurement is taken while only half of the viewing cone is covered, it might get a reading that is too long, and in the worst case a value that is too long but within the specified boundaries for occupancy. In this case the relay triggers and the incoming train stops too early. I have to think about how to eliminate this problem. One approach would be filtering the read values, but this would slow down the detection process as the result would have to be based on more than one readout. The other option is checking the flux value of the readout and only consider the distance measurement if a certain quality of the readout is detected. However, before I can do that, I need to better understand the meaning of the flux value, which seems to fluctuate quite a lot, so more research is needed. The other problem was the SG90 servo. I think I just have a bad lot of these servos, or I need to use a stronger type. The ones I use typically break down after about 2 hours of continuous use. Not a problem for a test, but unacceptable for something more permanent. But other than that, I think this initial experiment was quite successful, and here's the summary of the main insights. A simple layout animation for 2 trains can easily be done using DC power, a relay and 2 at-point detectors to change the polarity. The suggested layout with a siding and 2 trains traveling in opposing directions seems simple, but at the same time is complex enough to demonstrate more elaborated control concepts using DCC and JMRI scripting. By using a LiDAR sensor mounted on a servo, it is possible to create a software-defined universal occupancy detector, at least for G-scale. But I think it also would be possible to do it for HO. With just 2 sensor locations, the readout frequency for each position is more than needed for train control. With more positions and wider angle, there will be a slowdown. It remains to be seen if the performance will still be good enough to control the trains. Those cheap SG90 servos are not made for continuous operation. A higher quality drivetrain is needed to prevent frequent mechanical failure. Going forward, I will try to have more sensor locations and run the trains using DCC. I will also connect LocoNet to a PC and JMRI to see how the trains can be controlled using scripting. And if I can extend block detection to the other side of the oval loop, I will try to have a section with ABS signaling. So there is plenty of stuff to investigate and report in future videos. And that's it for today's video. I hope this information was useful or at least interesting for you. If so, you know what to do. Thanks for watching and see you next time.